Welcome everyone to lesson 1.11 in Precalculus. Today we're going to be talking about equivalent representations of a polynomial and rational functions. So let's get started, shall we? So when we talk about equivalent representations of polynomials and rational functions, what we really mean is that there are two major forms that these functions take. They either take factored form, which is where the polynomial or the rational is written as a product, or with the rational, a product, quotient, product of linear factors or non-factorable quadratic factors. So if it's a string of multiplication, you probably have factored form. Standard form, on the other hand, is when it's written as a sum, meaning addition, of monomial functions in descending order of their powers. So x squared, x constant, x cubed, x constant, all that's fine. And for rational functions, the polynomial on the numerator and the polynomial in the denominator are both in standard form. Why do we use these two major forms? Like, what's the benefit of one over the other? So that really comes into play with what you're trying to find. In factored form, it's really easy to find zeros, wholes, and vertical asymptotes for these functions, but you have to work a little bit in order to find the degree, the end behavior, the y-intercept, horizontal asymptotes, and slant asymptotes. So all of those take a little bit of work. Now keep in mind that some of these might not apply for polynomials, like there's no wholes in polynomials, for example. Where standard form, other information is easier to find, so you got to work a little bit harder for some of the others. What's easy to find in standard form is the y-intercept, the end behavior, the degree, horizontal asymptotes. What needs a little bit of work is zeros, wholes, vertical asymptotes, and slant asymptotes. So some of them need a little bit of work for both. Slant asymptotes need a little bit of work for both factored and standard form, although typically they're easier to find in standard form because we'll find out a little later. So let's look at two functions given to us analytically, one in factored and one in standard form, and see what we can pull out of these functions. So the first thing I'm going to do is I'm actually going to factor this function as much as I can, this f, as much as I can, to one, have the best of both worlds. I'm going to have both forms in front of me so I have an idea of what's going on here. So I notice that x is factorable out of everything. In fact, more than just x is factorable out of everything. 2 is as well, so I'm actually going to factor out that 2 as well, leaving me with that. And if I'm not mistaken, I believe that that is x minus 4 times x minus 4. So the degree of this function, which we can get from the standard form, is right here. It is 3. Its end behavior, remember, for polynomials, end behavior, we look at the leading coefficient and the degree to figure out what's going on here. I know that it's odd, so the ends are going in opposite directions, and leading coefficient is positive, so the right is going up, so the left must be going down. We need to write this in limit notation. So the limit as x approaches negative infinity for f of x is equal to negative infinity. The limit as x approaches infinity for f of x is positive infinity. Y-intercept, really nice. We plug in a 0 to the standard form where we look for the constant. It has no constant, so its y-intercept is y equals 0 or 0, 0 if you're looking for the point. Zeros, well, we want to look at the factored form. So we have a 0 there, 4 here, and 4 here. So that tells me that we have two zeros. We have a 0 at x equals 0, and we have x equals 4 with a multiplicity of 2. So that is going to come into play later. So where is f greater than or equal to 0? So this means that we need to look at what's happening for all of our parts. And we don't really need to do a whole lot of work if we remember what we've learned previously. So we're really looking at what happens between negative infinity and 0. 0 and 4, and 4 and infinity. We know that it's 0 at 0, and it's 0 at 4, but there's a multiplicity of 2 at 4. We also know from the end behavior that we're starting below, and we're ending above. 0 is multiplicity of 1, so the sign is going to change. And 4 is multiplicity of 2, which means the sign is not going to change. So our answer here is essentially everything from 0 onwards. So our answer would be 0 to infinity inclusive of 0. Even though we're dealing with multiple chunks, we can combine them because everything in our combination is included. So we don't have to say from 0 to 4 inclusive and then 4 to infinity not inclusive. We can just combine all that into 1. The next function we got to deal with is g, and g is written in factored form, so we can already tell what the zeros are. We're going to have a 0 at 0, a 0 at 5, and we have zeros in the denominator at -3 and +1. So its domain is everything except what makes the denominator 0, so -infinity to -3, -3 to 1, and 1 to infinity. Zeros, well, we already found those. X equals 0 and x equals 5. Wholes, we didn't have any common zeros in the numerator and denominator this time, so we have none. Vertical asymptotes, very nicely, we have 2. We have x equals -3 and x equals +1. Horizontal asymptotes, so we got to work for a little bit. I notice that we have the same number of zeros in the numerator and same number of zeros in the denominator, which means that the degree in the numerator and the degree in the denominator are the same. So we have to look at the ratio of the leading coefficients. We don't really know what those are. So we need to multiply the x terms in the numerator and the x terms in the denominator to find it. By multiplying the ones in the numerator, I get 3x squared. Denominator, I get x squared. The ratio of their coefficients would be 3/1. So the horizontal asymptote is y equals 3. The y-intercept. To find the y-intercept, we need to plug in 0. So I plug in 0 to numerator, I'll get 0 times -5 over 3 times -1, which is 0 over a number, which is just 0. So our y-intercept is 0, 0. Very nice, not too bad. Really just using the skills that we've had and looking at these two forms in their entirety. So here's a little bit of fun. We're going to expand some binomials. So we're going to take something that would essentially be a linear factor with a multiplicity of 2, 3, and 4, and we're going to expand those to see what the standard form would look like. Hopefully, we're going to see a pattern emerge. So if I expand the first one, I'm going to have x squared, and then, well, it might actually help us to break it down. We have x plus 5 times x plus 5. So we have x times x, which is x squared. We have x times 5, which is 5x. 5 times x, which is also 5x. And then we're going to have 5 times 5, which is 25. So we have x squared plus 10x plus 25. Cubed. Well, that's just squared with another factor, right? So this is x plus 5 squared times x plus 5. And we actually already know what x plus 5 squared is, so let's replace it. We know that that is x squared plus 10x plus 25. So what I'm going to do is give each of these terms an x, or multiply it by x, essentially. X cubed plus 10x squared plus 25x. Then I'm going to multiply each of the terms by 5. So we're going to have 5x squared plus 50x, and then plus 125. Add all of the like terms together, and we get x cubed plus 15x squared plus 75x plus 125. Then we'll do it to the fourth power, which is the third power times another one. So I'm going to rewrite what we have here. We have x cubed plus 15x squared plus 75x plus 125, and that is being multiplied by x plus 5. So we're going to multiply each of the terms by x, and then we're going to multiply each of the terms by 5, and we're going to see what happens here. So we should get x to the fourth plus 15x cubed plus 75x to the second plus 125x. Then we're going to multiply each of the terms by 5, so bear with me a little bit. We're going to have 5x to the third. We're going to have 5 times 15, which is, I believe, 75 as well. X squared. We're going to have 5 times 75, which I'm not going to lie to you, I don't know off the top of my head, which is 375. And then we're going to have 5 times 125, which is, I believe, 625, and I am right. I'm going to double check my 75 there, do 15 times 5, and I am right. Cool. Cool. All right, now we're going to add our like terms together here, and we're going to get our final expansion, which is going to be x to the fourth plus 20x to the third. That looks ugly. Let's fix that. 75 plus 75 is 150. X squared. 125 plus 375 is 500x, and then plus this 625. So if we're expanding binomials, we can do this. The problem with this method is that it is tedious and it is time consuming. So we can actually use a tool developed by mathematicians back in the 1100s and the 1000s, coined today after a mathematician in, I think, the 15 or 1600s. Don't quote me on that. I do know he's French. So we have Pascal's triangle. So again, it's named after a mathematician. He didn't necessarily discover it. He's the one that kind of popularized it along the Western world, so we named it after him for some reason. But what Pascal's triangle is it is all of the coefficients of a binomial with coefficients of 1. So if I had x plus y squared, well, that would be x squared plus 2xy plus y squared. If we look here, we can see 1, 2, 1, the coefficients. Let me do that in red for us. So this Pascal's triangle can really help us with expansion of polynomials and how to do them in a more efficient manner. You can do it without, as we just showed above, but this is really going to help us out. I have it right here. He's French and from the 1600s. Look at that. So if I look at Pascal's triangle, if I'm looking at the power, so this is x plus y to the power of n. This is when n is 0, n is 1, n is 2, n is 3, n is 4, n is 5, so on and so forth. How can we create Pascal's triangle? Well, if we look, the leftmost sides and the rightmost sides of each row have 1. Then the middle, or the second and second to last terms, have the n number. Where do we get the middle here? Where does this 6 come from? Well, 1 plus 1, or 1 plus, so 1 plus 1 is 2. 1 plus 2 is 3. 3 plus 3 is 6. 1 plus 3 is 4. So it looks like we can add the two numbers diagonally above to create the next number in the sequence. Now, if you have questions on building Pascal's triangle, make sure you ask me in class. But here we're actually going to use it to do two things. We're going to expand a very big polynomial, this degree 5 polynomial, and we're going to find the third term in a degree 6 polynomial, which is crazy. So let's start out with this one. So the first thing I'm going to say is we have this set up. We're going to have 1, 5, 10, 10, 5, 1. Then what we're going to do is we're going to set each of these numbers to a combined power of 5. So we're going to have 1, x to the 5th, negative 3, to the 0. The powers add up to 5. And then we're going to add 5x to the fourth, negative 3 to the first. And we're going to continue this down the line. So plus 10x to the third, negative 3 to the second, plus 10x squared times negative 3 to the third, plus 5x to the first, negative 3 to the fourth, and then finally plus 1, negative 3 to the fifth. Oh, I don't need that. If I figure out what all of these are, that would be the function in standard form. Remember that the 0 power means 1, so we don't really need, oh, let me write that over here, x to the 0, negative 3 to the fifth. 0 power just turns into 1, so we really don't need those parts. Now we get to play with powers. So the first term is 1x to the fifth, or x to the fifth. Really nice. Now we have a negative 3 here, so when we raise that to an even power, we got to remember that's going to turn positive. If it's to an odd power, it's going to remain negative. So negative 3 to the first times 5 would be negative 15. So that would be negative 15x to the fourth. Negative 3 squared is 9. 9 times 10 is 90x to the third. And you can see we're going to quickly get larger and larger and larger. Negative 3 to the third is negative 27 times 10 would be negative 270x squared. Negative 3 to the fourth is quite a large number. It is 27 times 3, which is 81. 81 times 5, well, that's 405. Positive, because it's to the even power. And then negative 3 to the fifth is 81 times negative 3, which would be negative 243. So that is what f of x is equal to. So f of x is equal to that huge thing. But, as you can see, even though that was a little bit of work, not nearly as much work as we put in before, right? Let's find the third term of this degree 6 polynomial. So let's write down row 6, which would be 1, 6, 15, 20, 15, 6, 1. The third term has the 15 here, so we're going to use 15. Now, we know it's going to be 2x to some power and 3 to some power, but which one's which? Well, I like to focus on the first one. We know that the first term, it's going to be at a degree 6. It's going to have a power of 6, and it's going to go down for each term. So it's going to have a 6 at 1, a 5 at 6, so it's going to have a 4 at 15. So if this is 4, oh, kind of moved while I was writing there. This is 4, then this has to be 2 to add to the 6. Then we can just do it out. 3 squared is 9, 2 to the fourth power. Well, 2 times 2 is 4, 4 times 4 is 16, so this is 16x to the fourth. Multiply 15 by 16 by 9, we get a huge number of 2,160 x to the fourth. It is positive, because all the numbers were positive, and that would be our third term in the expansion. Not too bad. The last thing to note for this part is that binomial theorem just basically states that each term in the binomial expansion has a coefficient in Pascal's triangle, and then each part is being raised to a power where those powers sum to the degree of the polynomial. Sounds a little technical. Promise it's not that bad. It's literally what we did in this part here. So now we're going to focus on those slant asymptotes I alluded to before in part 1. And we're going to try to find them. So we're going to find them graphically, and then we're going to figure out how to find them analytically. And I'm going to show you 2 different ways, and you can pick whichever one's your favorite. I do have bias here. I do have a favorite here. And we'll go from there. So a slant asymptote is always an asymptote in the form of a line. Remember that a line for us is either y equals mx plus b, that's in standard form, or it could be in point slope form, which is y minus y1 equals m times x minus x1. I do like point slope form a little bit more if I'm looking at it graphically, because it's nicer sometimes. But I'm going to stick with the y equals mx plus b, the slope intercept form, to kind of ride home what I'm talking about here and the connections between the two different forms. So for slope-intercept form, we need to know the intercept and we need to know the slope of our dashed blue line here for f of x. So first thing I notice is it has a y-intercept at 1, so b equals 1. And then we can look at the rise over the run for the slope. So we just pick two nice points. There's a nice point here, there's a nice point here, and I'm going up 1 and to the right 1. So the slope is 1 over 1, which is 1. Really simple question for the first one. So the slant asymptote is y equals 1x plus 1, or just y equals x plus 1. So graphically, not too bad. Really, you can just find the y-intercept, and you're going to be able to figure that out pretty nicely for the most part. And then you can figure out the slope by looking at two nice points and the rise over the run for them. If you didn't have a nice point, you can use point-slope form for graphically. Let's set it across like here. You really can't tell what that is. So let's use one of the nice points that we found before. If we use this point here, it has an x value of 2 and a y value of 3 for this point right here. So for point-slope form, that would look like y minus 3 is equal to 1 times x minus 2. Cool thing is if we simplify this, we do get back to slope-intercept form, which is the most simplified version of a line. All right, so how do we find this stuff analytically? Well, you have to divide. So multiplication, not too bad. Addition, subtraction have their iffinesses when it comes to fractions, but division, you either have to do long division or you have to do synthetic division. Long division is just like it was when you had numbers and you did long division with numbers way back in the day. So let's start with that one. We would write what we're dividing, x squared minus x plus 2, inside a quotient. And then we would put what we're dividing by on the outside. And then we figure how many times does what we're dividing go into what we're dividing, or what we're dividing by go into what we're dividing. How many times, and we're going to focus on the very first term here, how many times does x go into x squared? Well, it goes into it 1x times. So what I'm going to do is I'm going to multiply this entire thing here by x. That would be x squared minus 3x. Then we're going to take it away. X squared, take away x squared is 0. We did that on purpose. X minus negative 3x. When you subtract a negative, remember it's the same thing as adding a positive, which would give us 2x. And then we're going to drop down that 2. Then we're going to do the exact same thing. How many times does x go into 2x? Well, it goes in there twice. We're going to distribute that, and we get 2x minus 6. And we're going to take that away. Well, 2x minus 2x is really nice. It's 0. We did that on purpose. And then remember that we're, again, subtracting negatives, which is like adding a positive. So that gives us 8, positive 8. So we have a remainder of 8. For our slant asymptote, what that tells us is the slant asymptote is the equation we get without the remainder. So y equals x plus 2 is our slant asymptote. So that one's really nice if you have something huge being divided by something huge. You can kind of do it without having to think. It's a mindless algorithm, really. Synthetic division's a little bit different and has some nuance. So the first thing that we're going to do is we're going to take the denominator and set it equal to 0. So x minus 3 is equal to 0. We solve, we get x equals 3. And we're going to take that 3 and we're going to throw it in a box. Then I'm going to write the coefficients of each of the terms in the numerator. We have 1, negative 1, 2. So 1, negative 1, 2. And then I'm going to draw a line. What we're going to do is essentially we're going to do some repeated addition and multiplication. To start things off, you're always going to drop the first number. And then anytime we go from the bottom up, anytime that we cross this line, we're going to multiply by what's in the box. So 1 times 3 is 3. Then we're going to add, and that gives us 2. And then we're going up again. So we're going to cross that line. We're going to multiply the 2 by 3, and we get 6. Then we're going to add, and then we're going to put the last number in a box. This translates to the exact same thing as before. Y equals 1x plus 2 with a remainder of 8. So we got the exact same thing as we got before, just another way of doing it. Now, the key difference here between long division and synthetic is, yes, synthetic takes less time, but there are some problems with synthetic, and we'll talk about those in a little bit. And one major problem is you have to only divide by linear factors. You cannot divide by quadratics. Long division doesn't have that problem. What that means for you, it means for us, is that if you're dividing by a non-factorable quadratic, you have no choice. You have to use long division because synthetic division can only divide by linear factors. But if you have a factorable quadratic, you can just divide by each of those linear factors to get your answer in synthetic. So let's try out some and see what happens here. So I'm going to use synthetic mainly because I want to show off the problems with synthetic. That way, if you come across these problems, you can be well equipped to answer those problems. So the first thing I'm going to do is I'm going to take the denominator, 2x plus 3, set that equal to 0. X is equal to negative 3 halves. We're going to put that in a box, but it's a fraction. We got to remember that it's a fraction later on. So negative 3 halves, we have 4, 2, 7. We're going to drop the 4. 4 times negative 3 halves is negative 6. Add those together, we get negative 4. Negative 4 times negative 3 halves is positive 6. We're going to add those together, and we're going, oh, that's a negative 7. And we're going to get negative 1. So that would be our remainder there. So what does this turn into? Well, it turns into 4x minus 4 with a remainder of negative 1. But this doesn't make sense for our answer. It doesn't make sense because 4 divided by 2 is 2 and not the 4 we got here. So when you have a fraction, you have to be careful. So this is not the right answer. What we're going to do is we're going to take the denominator here, and we're actually going to divide our answer. We're going to divide our answer by that denominator. So we're going to divide all of our numbers by 2. So that gives us 2x minus 2 minus 1/2. No, minus 2 with a remainder of negative 1/2. So our slant asymptote would then be y equals 2x minus 2. So that's one problem with synthetic division, is if you have a fraction, you have to remember to divide by the denominator of that fraction. The next one comes up here. So 1, we have a quadratic problem. 2, we have a missing term here. We go from squared to constant. We're missing the x. So we have like a plus 0x. We got to remember that for later. That's actually a problem for both, but I digress. You got to make sure you pay attention to that. What we're going to do now is we're going to find the zeros of the denominator. Well, we can do that by factoring. We'd have 2x plus 3 times x. So our 0 is 0 and negative 3 halves. So when you divide by 0 with synthetic division, it kind of breaks all apart. So you can't divide by 0 either. So let's start with the negative 3 halves, and I'll show you a trick to handle the 0 in a little bit. So we're going to throw negative 3 halves in a box, and we're going to write out our terms. We're going to remember to write a 0 for the linear term because it's missing. 6, 13, 0, negative 5. So we're going to go about our process like normal. Drop the 6. Negative 3 halves of 6 is negative 9. Add those together, we get 4. Negative 3 halves of 4 is negative 6, which gives us negative 6. Negative 3 halves of negative 6 is a positive 9. Add those together, we get a 4 as our remainder. Remember we had a denominator here, so we have to divide all of these by our denominator, giving us 2, not 2, giving us 3, 2, negative 3, and 2 in a box. What this represents is, this is 3x squared plus 2x minus 3 plus, and then we divided by this term here, so plus 2 over 2x plus 3. So that's how we would technically write the remainder out. We don't have to put that r, we can just do the remainder divided by what we divided by. Now we need to divide this by x, so this entire thing is being divided by x. Since we're dividing by a singular thing, a singular term, we can distribute our division. So we can do 3x squared divided by x plus 2x divided by x minus 3 divided by x. Plus, when you divide fractions, remember you keep change flip or multiply by the reciprocal. So plus 2 over, well, x times 2x plus 3. Well, if I notice something here, these two don't simplify at all. And we're going to have an x in the denominator. So when we get really, really big numbers, those are going to turn into infinitesimally small things. They're going to essentially be 0. So we don't care about those, actually. Those, for our slant asymptote purposes, don't matter. These simplify, though. These simplify into 3x plus 2. Well, guess what? That is our slant asymptote. So not too bad. If we had a number other than 0, we would just do synthetic division with that number. But if you have 0, if you have just an x, you can use this idea, and it makes life a whole lot easier. So hopefully we found that there are some shortcomings with synthetic, but it's not too bad. The last thing we're going to do here is we're going to describe the end behavior of g using limit notation. We know that the end behavior mimics that of the slant asymptote, this line here. So we know that g is going to follow along the line y equals 3x plus 2 for values closer and closer to positive and negative infinity. So what does this line do? Well, the line goes up from left to right, which means it goes down from right to left. So the left, or the limit as x approaches negative infinity of g of x, is going towards negative infinity, and the limit as x approaches positive infinity for g of x is going to be positive infinity. We can also use what we remember about the polynomial and their end behavior to figure that out as well. So when you have a slant asymptote, you can just use that equation and the rules we learned way back when about polynomials and their end behavior and figure out what the end behavior of this function would be. Not too bad. So slant asymptotes only occur, they're special really, they only occur when the degree in the numerator is 1 larger than the degree in the denominator. Otherwise, you're going to get end behavior mimicking whatever that degree is left over. If it's 2 larger, it's going to mimic a quadratic. 3 larger, it's going to mimic a cubic. 4, quartic, so on and so forth. But slant asymptotes are a little special because they represent lines. They're just 1 larger. That is it for this lesson. If you have any questions, make sure you ask me. Otherwise, I'll see you in the next video.